Hello everyone. So in the last session we came to the point and I was explaining the correction factors. Okay, so there were two kinds of correction factors, alpha and beta. Alpha was kinetic energy correction factor and beta was momentum correction factor. Okay, so what was alpha? Alpha was actually kinetic energy for actual velocity, okay, upon kinetic energy for average velocity. Okay, so it was actually VQ into dA by VQ into A. This was the formula for kinetic energy correction factor, okay, alpha. And what is the formula for beta? Beta was actually momentum correction factor. Beta, it was V square dA upon V square A. Okay, so let's solve one question, okay, dealing with these correction factors so that the concepts will get more clear. The question says velocity distribution in rectangular channel of width b and depth of flow y naught is k under root y. Okay, so the depth of flow is actually a function of this y. Okay, so the question says calculate. Okay, so write down the question. Calculate average velocity and correction factors alpha and beta. So this is the question. So let's solve it. We have to calculate average velocity v. V is v dot dA integration upon a. This will be the average velocity. Okay, so what is the value of v? V is a function of depth, so let's put the value of v as k into under root y, which was given in the question. And what is the value of a small area? A small area will be, this is a rectangular channel section, so this is the width b. So for any element of dy, the area will be b into dy. Okay, so it will be b into dy. Okay, and what is the area? Area is b into y naught. Y naught is the flow depth. Okay, this is the integration sign from 0 to y naught. So let's solve this question. The constant terms will get outside, this b and p gets cancelled, so it will be k upon y naught into, this will be y raised to the power 3 by 2 upon y naught. So the average velocity, it comes out to be into 2 by 3. How come? Because when the constant term gets outside, it will be k by y naught into y raised to the power 1 by 2 into dy. Okay, so this comes out to be k by y naught into y raised to the power 2 by 3 upon 2 by, sorry, it is 3 by 2 upon 3 by 2. Okay, so this comes out to be k by y naught to y raised to power 3 by 2 y naught. We will putting the value of y naught into 2 by 3. So this average velocity comes out to be 2k under root y naught by 3. This will be the average velocity. Okay, so now let's proceed and find the correction factors. So the correction factor, category of correction factor will be alpha will be v cube into dA by v cube into a with proper suitable integration factors. Okay, so what was v cube? We just recently derived v cube. The value of v was actually this was k under root y and dA was b into dy, and what was the this v? This we derived as 2k by 3 under root y naught. Okay, so this comes out to be 2k under root y naught by 3 whole cube into b into y naught. Okay, so this alpha will be integration of k cube raised to power 3 by 2 into b into dy naught 2 by 3 k under root y naught whole cube b to y naught. This b and this b gets cancelled. Okay, taking out all the constant terms outside and integrating these terms, we will get the value of alpha comes out to be 27 by 20. Okay, you can carry out the integration process. Okay, and what will be the momentum correction factor beta? Beta will be v square dA upon v square a. So this v was actually k under root y whole square, dA is by naught by v square. In this is original v, this was 2 by 3 k under root y naught, 2k under root y naught by 3 whole square. Sorry, this was actually b into dy. Okay, elemental area b into dy, and this will be b into y naught. Okay, so solving this, beta comes out to be 9 by 8. Okay, so this was the question which was based on correction factors to alpha and beta. Okay, so let's proceed forward. We will see what is the next topic is continuity equation. Okay, so in case of a steady flow, the continuity equation will be same as we have learned in fluid mechanics, which was discharge equal to A1 V1 equal to A2 V2. Okay, what is A1, what is V1? Suppose we had a channel section where this was cross section 1 and this was cross section 2. The area of this cross section was considered to be A1 and the area of this cross section is considered to be A2. If the fluid enters with a velocity V1 and discharge or leaves the pipe with a velocity V2, then according to continuity equation the discharge is constant, so A into V is should be constant. Okay, so from this term we get A1 into V1 equal to A2 into V2. Okay, so this is not a new thing, you have already learned in fluid mechanics. Okay, the discharge here was constant, so the differentiation of the discharge with respect to the length of the pipe is 0. Okay, let's proceed forward towards uniform flow in channels. Okay, uniform flow, or maybe a steady flow. Okay, so in open channel we have a bed slope, in a bed where water is flowing. Okay, so if this is channel bed at a certain angle, this is channel bed, this is the water surface. Okay, so the hydraulic gradient line will lie at the water surface and the total energy line will lie above the water surface, total energy line. Okay, and this channel bed slope, suppose this angle is S0, the slope is S0, and the hydraulic gradient line, this angle is SW, and the total energy line angle is SP. And these SP, SW and S0 are equal, means the bottom slope of the channel, the water surface and the total energy line are parallel to each other. Okay, so you may write a point that in uniform flow in channels, what bed slope water surface line, it is also called hydraulic gradient line, and total energy line are parallel to each other. Okay, so write down this point, this was point number 1, and if we can write this according to the slopes, we can write slope of the channel bed should be equal to slope of the water surface should be equal to slope of the total energy line. Okay, let's move to our second point. Second point is flow parameters are constant at every cross section. Means if we have a channel's bed slope and the flow is toward this direction, then the flow parameters, what are flow parameters? Flow parameters are actually depth of the flow, means this one, the depth of the flow is constant. Okay, the velocity of the flow, the velocity through which the fluid or the water is flowing, the weighted area and the discharge. Okay, so what is basically flow parameters? Flow parameters are depth of flow, velocity of flow, discharge, weighted area, etc. These are called flow parameters. So the flow parameters in a uniform flow of channel remains constant, okay, at every cross section of the slope. Okay. So what is a uniform flow equation? Okay, uniform flow equation we have to study in two formats. One is Chassis equation and the second one is Manning's equation. So what is Chassis equation? Chassis equation defines the velocity for a flow, for a steady flow, as V equal to C under root R into S naught, okay, where C is Chassis constant. It will be given in the question. R is hydraulic radius and S is slope of bottom of channel, okay. So we know that from Chassis equation V equal to C under root RS. We also know that discharge is equal to area into velocity. So finally we get discharge equal to area C under root RS. Okay, we have to remember this formula. Okay, this is from continuity equation. Okay, let's move towards Manning's formula. According to Manning's formula, the velocity of the flow is given by 1 by n, r raised to the power 2 by 3 and s raised to the power 1 by 2. Here n is Manning's coefficient and r and s are the same thing. R is hydraulic radius and S is channel bed slope. Okay, so according to Manning's formula, we have V equal to 1 by n into r raised to the power 2 by 3 s raised to the power 1 by 2. So the discharge will be A into velocity, so it will be A into 1 by n r raised to the power 2 by 3 s raised to the power 1 by 2. This is the value of discharge. Okay, this will be the value of Manning's coefficient, and we have already studied Chassis coefficient. Okay, so let's move towards next topic. Next topic is most economical or maybe most efficient channel section. Okay, if we have a certain channel section, suppose that it is a channel which is rectangular, which has rectangular cross section. Okay, this channel may be having a circular cross section. Okay, so there are different shapes of channels. So we need to define when that, if the channel is rectangular, then what should be the condition so that it is most economical or most efficient, and if the channel is of certain shapes, maybe circular, maybe triangular, or maybe trapezoidal, so what is the condition so that it is most economical and most efficient? Okay, so what is the meaning of this most economical and most efficient channel section? Okay, a channel section is said to be most efficient if it can pass maximum discharge for a given cross section. Okay, what do we need? We need maximum discharge, okay, for a certain cross section. If we have a channel of any kind of shape, then it will be most efficient if a maximum discharge is required, okay, for the certain purpose. Okay, we always need maximum discharge. Okay, so what should be the condition of maximum discharge? Okay, we know that discharge is equal to area into velocity. Okay, so if we use Manning's formula, then the discharge will be equal to A into 1 by n r raised to power 2 by 3 and s raised to power 1 by 2. Okay, so if a cross section area, we have a certain cross section area, then A is a constant and channel bed slope is constant, and this Manning's coefficient is also constant. So discharge will be maximum when this value of r will be maximum. What is r? R is actually hydraulic radius. Okay, so for Q to be Q max, R should be maximum. Okay, so what is R? R is weighted area by weighted perimeter. So for R to be maximum, we need perimeter to be minimum. Okay, are you getting it? For maximum hydraulic radius, this is inversely proportional to the perimeter with weighted perimeter. So in order to R to be maximum, we need perimeter to be minimum. Okay, so this is the condition. You need to remember this condition. Okay, the weighted perimeter should be minimum. Okay, so while we will deal with certain kind of sections, rectangular section or trapezoidal section, we always need to minimize this perimeter. Okay, by differentiation. But while minimizing this perimeter, we will increase the value of R, which will accordingly increase the value of discharge. Okay, so let's deal with firstly a rectangular section. Okay, we have this rectangular section with width B and the level of water is, suppose, y0. Okay, this is water. So what is the condition for which this rectangular section is most economical or most efficient? Okay, so let's derive this formula. We need to minimize the perimeter. Okay, so first let us find weighted area. What is the weighted area? This is the weighted area, this amount. Okay, this is the weighted area. What is the value of weighted area? A, it is B into Y. Okay, what is weighted perimeter? P is this one plus this one plus this one. Okay, so this is B plus Y plus Y. It is B plus 2Y. Okay, this is the value of weighted perimeter. Let's derive the value of B from this equation. We get B equal to A by Y plus 2Y. This is the value of perimeter. We need to differentiate. Now we need to differentiate this value of P and will work according to that. Okay, so we have P equal to A by Y plus 2Y. So now for discharge to be maximum, perimeter should be minimum. Okay, so dt by dy should be equal to 0. So we will differentiate this P with respect to Y and we'll see the results. Okay, so differentiating dP by dy equal to 0, we get minus A by Y square plus 2 equal to 0. Okay, this gives A equal to 2y square. Putting the value of A was B into Y equal to 2y square. So Y comes out to be this Y and this one Y gets cancelled, and then Y comes out to be P by 2. So this is the first condition for which our rectangular section is most economical. So what do we conclude from this? Y equal to P by 2 means this was B and this was Y. So the depth of the flow, this Y, should be half of the width of the section. Okay, so if we write in a language, for maximum discharge, the depth should be half of the width of the channel section. Okay, so this was the condition for rectangular channel section. You should write one point in note that most economical rectangular channel section is square section. Okay, a square section will be the most economical rectangular section with means the water flowing with half depth. Okay, there are certain more points to be remembered for a rectangular section to be economical. Okay, then properties of economic rectangular section. Okay, so first point should be area is equal to 2y square. Second condition was perimeter equal to 4y. Third condition is hydraulic radius should be half of the depth, and hydraulic depth should be y. And the last point is top width equal to 2 times y. Okay, so these are the conditions for rectangular section channel to be most economical. Okay, let's move forward and let's deal with most economical trapezoidal section. What is a trapezoidal section? Trapezoidal section is looks like in this manner. Okay, This is the side slopes. These are called the side slopes of the channel, and this is the width of the channel. The water is filled up to the brim. This is the water level. Okay, so this is the width, this is the depth, and the slope of this section is m/1, means m horizontal is to 1 unit of vertical. This is the slope. Okay, so if we this depth is y and the slope is m, so the length of this part is y into 1 plus m square. Okay, so this length is y into 1 plus m square, and this value will be my. Okay, this value is my, and here it will be value of b, same. Okay, so we have analyzed the trapezoid. Okay, how the trapezoid dimensions of the trapezoid channel. Let's move again and analyze the most efficient channel. Okay, so we have this trapezoidal section with the water top surface over here, and this is width, this is y into under root 1 plus m square. Okay, so what is the wetted area is half into sum of parallel sides into distance between them. This is the area of the trapezoid. So what is the sum of the parallel sides? Is b, and this parallel side is b plus my plus my. This distance is my. Okay, so it will be b plus b plus 2my. And what is the distance between them? Distance between them is the depth of the flow into y. So wetted area comes out to be b plus my into y. Okay, this will be 2b, b plus b 2b, and when we take out this 2 common, this 2 and 2 gets cancelled. Okay, so we will be left with only b plus my into y. This is the wetted area of the trapezoid section. Okay, now let us derive the wetted perimeter. What is the wetted perimeter? Wetted perimeter is nothing but the surface surrounding the, this is the depth, so this one plus this one plus this one. Okay, so wetted perimeter is b plus 2 into this was y into 1 plus m square. So this y plus y into 1 plus m square under root plus this y into 1 under root 1 plus m square becomes 2y into 1 plus m square under root 1 plus m square. This is the perimeter of the channel section. Okay, so we had this wetted area equal to b plus my into y. So put this value of derived value of b from here and putting over it here, we will get a by y minus my plus 2y under root 1 plus m square. This is the value of wetted perimeter. Okay, now what do? We will differentiate this wetted perimeter with respect to y and derive the results. Okay, so dp by dy equal to 0, we will get, okay, here we will get minus a by y square minus m plus 2 under root 1 plus m square equal equal to 0. Okay, put the value of a should be minus b plus my to y square into y minus m plus 2 under root 1 plus m square equal to 0. Okay, so if we go on deriving, we'll get the results as b plus 2my equal to 2y under root 1 plus m square. Okay, so what do we conclude from this? What is b plus 2my? b plus 2my was this was the value of b, this was my, and this was my. So what is b plus 2my? This is the width of the top surface of the water. Okay, so what do we conclude here? We conclude that top width of the trapezoidal section is twice the sloping side. Okay, this is the conclusion for trapezoidal section. Okay, so what is the hydraulic radius? It is weighted area by weighted perimeter. What is the weighted area? b plus my into y. What is the value of weighted perimeter? b plus 2y into under root 1 plus m square. Okay, so it is b plus my into y. Okay, and from the previous results we can put b 2y into 1 plus m square as b plus 2my. This means b plus 2my. Okay, from where do we put? We obtained the result previously, that b plus 2my is equal to 2y into 1 plus m square. Okay, so this 2 into y plus 1, 2 into y under root 1 plus m square is equal to b plus 2my. So we put this value here, we can obtain. Okay, so the result came out to be r equal to b plus my into y by 2 into b plus my. So this b plus my and this b plus my gets cancelled, and hydraulic radius comes out to be y by 2. Okay, so we have two conditions here. The first condition was top width b plus 2my was equal to twice the side slopes. Second condition we obtained was hydraulic radius should be half of the depth. Okay, let us obtain one more result. Best side slope for most economic section. Okay, so what is the best side slope? We know, we have obtained that p was equal to a by y minus my plus 2y into 1 plus m square. Okay, let us consider this equation 1. Now for most economic section, we have dp by dy equal to 0. So now differentiate this term, we will get dp by dy as minus a upon y square minus m plus 2 into under root 1 plus m square. Okay, we get this thing. Then dp by dy should be equal to 0. So now equate this term equal to 0. We get minus a by y square minus m plus 2 under root 1 plus m square equal to 0. And here a comes out to be 2 under root 1 plus m square minus m into y square. Consider this equation 2. Now put this value of equation 2 in equation 1 that we have considered previously, which was p equal to a by y minus my plus 2y under root 1 plus m square. Put that, this was equation 1. Put the value of equation 2 in this equation. We will get p equal to 2 under root 1 plus m square minus m into y square by y minus my plus 2y under root 1 plus m square. Okay, so the value of p comes out to be, this y gets cancelled, 4y under root 1 plus m square minus 2my. Okay, so the perimeter obtained is 4y into 1 plus m square minus 2my. Now dp by dm equal to 0. Okay, we get take out this y common from here. We get y into 4 1 by 2 under root 1 plus m square into 2m minus 2 equal to 0. Okay, here y is not equal to 0 means the depth of the flow is not equal to 0, so this term must be equal to 0. Okay, so 4 into 1 by 2 under root 1 plus m square 2m minus 2 equal to 0. Let's solve this. We will get 4 1 by 2 under root 1 plus m square into 2m minus 2 equal to 0. This 2 gets cancelled, means 2m by under root 1 plus m square equal to 2. Sorry, this is equal to 1. This 2. Okay, so 2m equal to 1 plus m square means 4m square equal to 1 plus m square means 3m square equal to 1, so m equal to plus minus 1 by root 3. So the value of m should be 1 by root 3, means tan theta should be equal to 1 by m, means 1 by root 3 equal to root 3. So tan theta is equal to root 3 means theta should be equal to 60 degrees. So for a most economical trapezoidal section, the value of m means this slope m should be equal to root 3. Okay, or the angle should be equal to 60 degrees. Okay, this is the third condition. Okay, for the trapezoidal section. Okay, this, so now in this section, for the most economical section, we learned rectangular section and trapezoidal section. Okay, in the next session we will solve some numericals based on this rectangular section and trapezoidal efficient section, and we will deal with circular channel section and triangular channel section. Okay, so this was all for now for this session. Okay, thank you.